Good evening, everyone. After a summer hiatus, I would like to welcome you all to the EOL seminar series. To jumpstart the series, it is my pleasure to introduce our speaker, Dr. Javier Fochesatto, who is a professor at the University of Alaska Fairbanks in the Department of Atmospheric Science. Javier wears many hats. He chairs the Department of Atmospheric Sciences at the University of Alaska Fairbanks. He is the director of the Alaska Statewide Science High School Symposium. He is the editor-in-chief of the Journal of Atmospheric and Oceanic Technology, and he is on the editorial advisory board of the Review of Scientific Instruments. Dr. Fochesatto is also the University of Alaska Fairbanks' member representative for UCAR. Dr. Fochesatto started his education in electrical engineering at the National Technical University in Buenos Aires, Argentina, that arced into a PhD in physics at the Sorbonne University in Paris. His research focus has been within the atmospheric boundary layer, examining turbulence, mesoscale dynamics, and pollution using instruments, experiments, and models. This all ties into his talk today, examining radiative boundary layers in the dark and cold atmospheres, using the Alaskan winters as the main stage to examine the formation of temperature inversions and their impact on surface energy balance and turbulent fluxes. We are using Slido to pose questions that you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen if you scroll down. Please do not be alarmed if you do not see your question. We are archiving all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. Dr. Javier Fochesatto, we welcome you to EOL, and the virtual stage is now yours.
Thank you so much, Jackie, and thank you, Brett, for organizing and setting up the communication. And thank you, y'all, actually, and Vanda, for actually, I didn't realize that I'm the first in this series, but anyway. So yes, radiative boundary layers. So this is an important topic, actually, because probably it's a topic that actually mostly concerned with instrumentation. But now we are actually looking at more closely to see how we can actually enter into the improving the modeling aspects of these boundary layers. So the photo that you are seeing there actually is a typical photo from the ALPACA working group, actually. And so you have seen this from the IGAC probably meetings, and so it illustrates from the hills actually the bay or the bowl of the Fairbanks area actually. And so but I promise I have a little bit more complicated photos to show. So the flow of the talk actually today, I will talk a little bit about the problem, and so I will refer to a previous experiment called WBLEX, Winter Boundary Layer Experiment, which was an experiment that I've done with a couple of students and a couple of colleagues, but mostly looking at boundary layer heights and ventilation related to, obviously, to mesoscale modeling, but I was more concerned about the problems of radiation and dynamics. And so as we go along, I will point into the multi-layer structure of the PBL, and as well as into two significant aspects of this, which is the surface base inversion, SBIs, and then the radiative forcing of those elevated inversion, EI layers. Then I will show some of the recent experiments that we've done in terms of surface energy balance and some elements related to shallow cold flows and some large eddy turbulence. To end this seminar, I will look into I will show you the new experiment that we are proposing for this upcoming winter. So ALPACA, IGAC-ALPACA actually is Alaskan Layer Pollution and Chemistry, and so analysis actually, but that analysis, although in the cold and the dark, and in terms of atmospheric chemistry, my colleagues, which probably will be here in the seminar, Bill Simpson and Jinkyu Mao from the UIF, but also all the colleagues that are also participating in this ALPACA project, actually, are very interested in the chemical processes, the chemical composition of particle matters, and processes within the cold and the dark atmosphere. However, all of this has to bear the very complex and challenging PBL. So some of the bullet points are laid down there somehow describe the complexity of this boundary layer. So basically no solar radiation, just a little spikes of in the middle of the winter, you can see about 15 watt per square meter, but very short, nothing really prominent. Extreme cold temperatures, ice and snow covered surfaces, and outstanding anticyclones. All this combo leads to the formation of multi-layer inversions. So this structure obviously impact the radiative fluxes and therefore impact the energy balance, and obviously as a result, depending on the flows, the surface turbulent fluxes. So the understanding of these dynamics within the PBL to connect sources with measuring points actually that are related to microphysics of aerosols or chemicals requires a deeper understanding. So because of that, so we are proposing, an experiment where we can actually determine surface processes, radiation and turbulence, and then also determine structural parameters of the boundary layer and some other parameters like large area average surface fluxes, so that we can actually force the mesoscale model and Cal-Val those models so that's why I call this a closure experiment. So just a little bit overview of the area where we are. So the picture on the left actually is what describes the Tanana Valley here, where most of the flow that defines this area is defined by the presence of the Tanana Valley. However, the population around that lives in Fairbanks and where the air pollution is, so is around this area a little bit north of what it is indicated as a Tanana Valley. In addition to that, we have another valley that has an extension in the northeast direction, actually Goldstream Valley called here, that is about 10 kilometers. And that is a valley that remains in the dark after the mountains, because the mountains are, in orientation north-south. And that is very important in terms of some sub-mesoscale flows that we see near Fairbanks. So during WBLEX, we set it up here, a large aperture scintillometer, a Doppler sonar, some med towers, and sonic anemometers, and to determine some of these characteristics that I will proceed to show. So now related to the current measurements and the measurements that are done in the National Weather Service, for example, here in the map on the left, actually I'm showing the farm where the UIF campus farm where we developed the experiment, but also about in a straight line, like 3.5 kilometers, we have the airstrip actually, which just right beside is the National Weather Service facility for continuous radio soundings. So it is important to visualize that what obviously, if I have to initialize a model, I will use the data sets that exist for the National Weather Service. However, these data sets might entail dynamics and thermodynamics on the model output that might not be necessarily representative of the processes that are in the Fairbanks area, especially when it comes to areas close to the hills here, because of the presence of northwestern, in this case, for example, intermittent flows. So here, for example, are some summary results that we have provide actually combining Doppler acoustic sounders and radio sounds in the National Weather Service. During WeebleX, what we have done was to have a period of time where the Doppler sonar was collocated to the radio sounding, and then we have another period of time where the Doppler sonar was at the campus of the university, and so to be able to compare. So in the two figures that you see on the top, actually, these are the wind speed and the wind direction, but taken from the radio sounding observation within the PBL. So for a period of time, you look at the PBL height, and then you determine the wind speed and the wind direction within the PBL. The same in the bottom plots, actually, we're seeing the wind speed and the wind direction, but near the foothills. Obviously, we are seeing an outstanding difference in wind direction presence in terms of what is the flow that aims the boundary layer in these two places. But at the same time, in the figures on the left, actually are the histograms for wind speeds, where we see a significant, not significant, but there is a difference in the wind speeds, obviously lower wind speeds within the foothills, obviously due to the topography. So these results were because we were collaborating also with the Aeolus, the LiDAR in space, actually, and we were processing this data also to look at what is the data distribution within the PBL and in the free atmosphere, because Aeolus actually arrived to put 1 point in the boundary layer. So because also we were a little bit suspicious about what the sonar were actually delivering. That's why we collocated for a certain time. And so the first bullet actually described the collocated observations. We found in the free atmosphere actually a difference in 1 meter per second maximum, while within the boundary layer we have an underestimation of 0.5 meter per second maximum. Yeah? And wind directions, just a little bit of a divergence in about 6 to 10 degrees, actually. Another thing that we were interested in, especially because there has been several articles describing in the Barrow area, actually, about the surface-based inversion and about probably the intermittency of those layers. I was interested in seeing, what the Doppler sonar actually can deliver around plus minus a certain amount of time around the 0 UTC and the 12 UTC sounding. And there are some differences as we continue doing measurements around those radio soundings, which actually talks about the variability of the flow, but at the same time about the persistence of those inversion layers. Comparing these two sites, actually, it is clear that there is a difference in between what the flow that we are seeing inside the bowl of the Fairbanks area and compared to the value. And the last bullet actually relates to how how this kind of observation can be assimilated by the space platform, Aeolus in this case. And so so basically, as you can imagine, if you take ground-based observations to assimilate, so the idea is that Aeolus actually measure the longitudinal component of the wind and then use the model, the ECMWF model, to assimilate that component of the winds and then reproduce the full wind field, actually. And so basically, there is a need to consider topographic forcing and obviously probably an adequate subgrid parameterization to actually assimilate values that might be influenced by topographic elements. Anyway, so let's talk about the complexity that represent the radiative boundary layer. So this is a listing that is not necessarily exhausted, but basically we are in boundary layers that are in the middle of the winter when we know shortwave downwelling and or approximately short downwelling radiation that is approximately, but most of the time less than the absolute R net. Okay, and so basically, this is a situation where the energy balance is dominated by long wave radiation. Okay, so obviously there is no latent heat, because if not even there is a sublimation, because there is no short wave incoming, and sensible heat, actually maximums that we have retrieved are rounding the 20 watt per square meter, no more than that, but there may be some situation where you get into the 30s whenever you have wind blowing within the boundary layer. So wind speeds in the PBL, most of the time 1 to 2 or even less than 1 under stagnant condition in AC anticyclone situations. In addition to that, when a surface-based inversion develops, there is 85% of the time we have a multi-layer structure. All this analysis is in a JAMSI paper that we published in 2013. In addition, I think that this latitude is very interesting, because this latitude is in the path of the migration of the Arctic front, and so it is very typical from here in Fairbanks that whenever we look at the south and we see the Alaska ranges, the Arctic front is down the south, and whenever we see weather, it's because the Arctic front is migrating towards the north. So therefore, the cycling of the deep cooling events actually is mandated or dictated by the Arctic front, which is regulated by synoptic meteorology. So these elements has been summarized very long time ago, 1968, by Sue Balding, actually one of our faculty, but also very recently by John Cassano and Elizabeth and Matt Nolan, actually. Where there is this is an article in JGR that actually describes very well the dependence of the air temperatures with the synoptic components. By the way, so those air temperature series verify deep cooling events, actually, that are the ones that we are looking at for pollution and also for better understanding the boundary layer. But at the same time, I just have to indicate that normally those periods were historically about 5 to 7 during the winter, and now we are getting into the 2 or 3 per year. So talking about this complexity, we are on top of that, whenever the temperatures are going below and below -20, -30, -40, so we are looking at ice fog as well. So the picture on the left actually is from the Geophysical Institute, from the western side of the area of the campus, and we are seeing 2 plumes actually coming out. One is from the UIF campus, and the other is from the borough, from downtown. And as we look on the south, we're seeing the plumes drifting that are above the surface-based inversion, but between but below the elevated inversion. And then these are the plumes already that in many cases are seen in the airport, and because obviously these are 20 degrees C emission that enter into an ice saturated environment and therefore will form ice. And so anyway, so switching into what it is, the multi-layer PBL, what we call that, is the presence of a temperature profile, as it is indicated here, temperature and height in the vertical. And you see 2 inversions here very clearly defined. One is what we call the surface base inversion, because it is anchored, the base of the inversion is at the surface, and another one that has a base at a given height and a height defined by the change of the slope on the DT-DC gradient. So we in a sense, there is another factor that comes into play here, which is related to a stratification layer. So this inversion, the SBI, is not just as simple as it is with one temperature gradient, because obviously you can imagine that the atmospheric composition here is extremely variable. And so in addition to that, in one of the works we've done, we have investigated the elevated inversions and their nature, and we come up with 2 kinds of very well-defined elevated inversion, one due to anticyclones, which is basically when you have the anticyclone, basically you have an adiabatic compression in upper levels, and therefore you create an inversion. And then there is another condition by which you have an inversion, or create an inversion, where you produce a advective motion actually, and that is the one that I call EI cyclone. And then there is obviously, if you are monitoring 0 to 12 systematically in an NWS station, you are going to be seeing transient situations. But the most important thing here is that actually the presence of that elevated inversion not only impose an upper level capping to the pollution dispersion, but at the same time imposes an air mass that will be a radiative body that will interact with the surface phase inversion and the surface fluxes. And if you can imagine, if it is the case of an anticyclone, we are just right on saying that that is a dry air mass, while if it is a cyclone, then it's going to be a moist air mass. And therefore, the LW downwelling would be playing a significant role here. In order to investigate those temperature structures, there has been some algorithms that has been developed over time, but I have developed a different kind of algorithms in which I go with a fitting and refitting process in a multilinear segment, so that I can basically identify all the layers that exist within a given profile. So this method is published in the AMT, and so basically it can take temperature profiles, and then you have to apply a criterion to actually deduce what it is a surface-based inversion, what it is an elevated inversion. But through that, we arrive to identify the time series of SBIs and EI. So processing the Fairbanks data, actually, we arrive to, for example, in this case, I'm showing the statistical distribution of SBIs and the first elevated inversion, which obviously has a prominent mode in around 1000, while the second elevated inversion, which has a little bit of a, obviously, a much asymmetric distribution, actually, and obviously located at a higher level, actually. So the table underneath actually shows the mean and the median characteristical parameters of those inversion heights. And so just for everybody, is 300 meters, 350, 370 for the SBIs, while 1,000 meters, 1.2 kilometers is the presence of the first EI. This is very important to realize because when we think about modeling of these aspects, probably any mesoscale model, which I have also seen downscaling climate model outputs that actually are able to track the synoptic inversion. However, the surface-based inversion is something that is very difficult to realize in the models. And also, in addition, by thinking about the fact that actually we have to be able to determine SBIs in the context of EIs, therefore there is a need to have instruments that actually can profile all these cross section. Okay? So in looking at the origin of the EI layers, and the reason for that is because the thermodynamic of the air mass that entrain the elevated inversion layer will have a significant effect on the surface. That is why we went into this type of analysis, where identifying the base of the inversion and the top of the inversion, we can look at the dew point temperature across that layer. And we have done verifications of that using obviously synoptic charts actually, and to actually come up with a very simple definition by which we can identify those situations by being warm air advection or cyclones whenever you move from the base of the elevated inversion to the top and you see that the dew point increase, or the opposite, when you see that the dew point decrease, then you are within an elevated inversion produced by an anticyclone. As a result, what we are seeing is that 35.8% of those EI layers are defined as an AC condition with a 1.2 kilometer height, while the 22% of those elevated inversions are due to warm air advections and with a lower height. There is a remaining that are related to synoptic transients, obviously when you monitor 012 systematically every day. And there are some other unclassified elements, about 18%. But here's the thing. There is an interesting result when you observe the statistical parameters of the elevated inversion heights, actually, because when you look at the dispersion of the EI's anticyclones, you're going to see a larger dispersion compared to the EI cyclones. And the reason is the physical mechanism that give rise to those elevated inversions, namely that when you have an anticyclone, the air mass is wobbling and compressing down around the area, and therefore if you sample 012, you're going to see that air mass at different heights. While whenever it is an EI that is generated by a cyclone condition, then it's going to be a penetrative flow that most of the time will be around the similar heights. So again, and in my second bullet in red, now we need to determine this, the SVI profile in temperature, but also the EI layers. And I hope that with the new acquisition we have funded by NSF, the microwave radiometer will be, which is specially adapted for very cold atmospheres, will be able to review, to give us the temperature at those heights. Moving on, I'm going to describe here another set of experiments that we have done within WBLEX. So another student, Julie Malinkovsky, actually, have done those lunches. She was trained by the National Weather Service to do those lunches and incorporate those lunches within the system, actually. So in this case, this was the transition between RS-80 and the Lockheed Martin GPS soundings. And so that's why we have a series of episodes of records where we were launching every 3 hours. Obviously, the conditions are really very complex. Nowadays, the NWS uses the Vaisala system, actually, which is an automatic system. But in this case, you know, it was necessary to go out and do that. As you can see, these are basically the temperature profiles on the left. In the central plot are the wind speed. And then on the plot on the right, you have the wind direction across the boundary layer and in the free atmosphere. So the flow is very well defined from one north and eastern veering toward eastern directions. Wind speeds are really very, very low in the boundary layer, but there are some pulses overnight that within the boundary layer that introduce mixing. And in some cases, slows down the cooling. But overall, and so you have bullet points here, but overall, what we have found within the buildup of the surface phase inversion is that there is 2 phases by which this is done. The first one is a rapid cooling at the surface over a shallow surface phase inversion. And then after a certain point, which is basically determined by the composition in the atmosphere and the open, the open sky, the cooling rate actually. So then there is a growing phase of that SVI height actually. So in a sense, it's a surface aerial cooling that then is followed by a vertical columnar cooling actually. So obviously we have like 5-6 cases that are described in this paper that is cited down in the bottom. And we have also verified the presence of the cooling rate actually slows down because of pulses, because of wind pulses that appears on the either in the free atmosphere or within the PBL actually. And so, but I will say that in order to actually get a handle of this build-up process of the surface phase inversion, there is a need not only to do surface fluxes and radiation fluxes at the surface, but also in the vertical. And that is what we are going to look into. Another aspect of this surface-based inversion, which is very, very interesting, because obviously the buildup of the SBI, actually, especially the SBIs, when they build up, they are shallow between 5 to 7 p.m. actually, and there is the time where everybody goes home, and therefore the air pollution picks up at that time. So, however, the breakup of surface-based inversion or breakup of surface layers inversion is something that is known, and basically several researchers, I can name Dave Whiteman from Utah, and also Larry Moore from Oregon State. But at those latitudes, this breakup of surface-based inversion, which is also the same thing we have, but in the late winter, after the third week of February, we start seeing a diurnal cycle that actually, but still is under snow, which also, the heat capacity is different from being an uncovered surface. In this case, what I wanted to point out is that there is another kind of mechanism that actually produces breakup of surface-based inversion, and this is the one that is illustrated here. With a sequence of radio sounding profiles, where you see a strong surface-based inversion that is over time build up and warms up, and then still and is there, but there is an elevated inversion layer that builds over time that actually end up warming the entire surface. So these are really very important processes, because actually from the air pollution process, you're going to have a layer that actually will communicate local home heating sources with industrial plumes and power plants, actually, in a single mixing process. But at the same time, for boundary layer dynamics, it is very important, because obviously the surface has become the surface turbulence regime has changed, and another work that we have just presented at the beginning in January in the AMS, we have computed the changes in the surface fluxes spectrum as the warm advections comes in, and so we're looking into publishing those results. Another element here that comes out from some processes that we have, studies that we have done. So this is the Doppler sonar actually looking at the shallow cold flows actually, and then the second plot is the BLS compared to the EC fluxes. And what we have looked into this is the case where we have drainage flow that are intermittent, and so one of the parameters that comes out there is that we have seen a differences between what captured the scintillometer and what captured the EC flux, actually, the eddy covariance fluxes, and there is a question there about from where those large eddies comes into the surface layer, and I can if anybody's interested, I can describe more in detail. So in early ALPACA 2019, we developed a little bit of a pre-ALPACA experiment, and so here is the photos that you see when the anticyclone start to build up, and so here are our French students in the field, so setting up the laser scintillometer and some of the eddy covariance towers. So here's one episode that is on the top is the LiDAR, the two wavelength LiDAR system from LATMOS, actually describing the vertical profile, and in the certain area, in the central area, we are seeing the development of the anticyclone. So interesting, the long wave fluxes here, long wave upwelling, downwelling, actually, they tend to have a maximum differences here in the central area where the anticyclone develops, and those differences are in a range that are different from the maximum sensible heat flux that we can get. So basically, we are so there's a problem with closing that energy balance. So on one side, we can develop between 20, maximum 20, but also sometimes 30 watt per square meter sensible heat flux. But on the other side, we have an imbalance of 30 to 40 to 60 watt per square meter, and this is something that we need to look into. In addition to that, this is the other LiDAR, the MPL net actually, that is on the West Ridge, that is seeing basically the same feature that is seeing the other LiDAR, which is located in one of the locations for one of the sites for ALPACA. So here I'm looking at the surface energy balance because we got interested in seeing those aspects of the energy balance, and how they play in two sites. We have one is the UIF campus farm, which is on the west side of the area or ALPACA, but also like less than 2 kilometer difference. Yeah, less than 2 kilometers. We have another site that is the one called AmeriFlux site, and so this is in the boreal forest in discontinuous permafrost. So the time series that I'm showing there is the wind direction and wind speed actually. So there is some in the boreal forest side actually, there is some intermittency in the wind direction actually, but the winds are significantly lower than 1 meter per second. While on the other side, in the UIF farm side actually, the winds are like 10 times higher with a wind direction that is more clearly defined. Now here are the long wave downwilling. Again, when it says here Smith Lake actually is the boreal forest actually. The blue lines are the boreal forest, and the orange lines are the university farm actually. And we can see that the large divergence between upwilling and downwilling in the university indicates a larger exposure to the deep cooling, but also the blue line, and this is something that we need to investigate, also because of the differences that we see in the downwilling, because obviously the sky, you may say, well, but the sky in 2 kilometers will not be able to change that much, but actually you have recirculation plumes that obviously will impact the Smith Lake or the AmeriFlux side actually. So the second plot is basically temperatures across the area of the proposed ALPACA experiment, and more or less we have with more or less intensity in the differences in the vertical, we have approximately similar features. Here it comes with the radiative fluxes, and again I will say that the sensible heat flux in both this is the orange line actually for that anticyclone period, we are seeing even less than 20 watt per square meter, and here we are seeing a little bit over 20 watt per square meter, but the difference in the net radiation is larger than that. So because of that, we are proposing actually an experiment where we can actually think about how we can actually look at those processes on the net radiation and long wave upwilling, downwilling in the vertical and around the areas where we measure, so that we can assess these changes in energy balance. So the proposed experiment actually contains, this is the area where we have LiDARs and boreal forest here, and then we have the farm here. That's another point, and then here is a large forested area, which is an open field where we're gonna develop another experimental turbulent sensing, and then this is the area where most of the ALPACA chemistry will be happening, and in there we have an open field that's called soccer fields, where we're gonna concentrate all the profilers, the microwave radiometer, the LiDARs, and the radar, so that in addition to surface turbulence and radiation, so that we can get a handle of the model. So here are the sites with the coordinates and some of the people that are operating. When we say ALPACA super site, means that there's going to be not only dynamics but also a lot of chemistry, and so So we have one site in North Pole, which is a city probably 15 miles south of Fairbanks, actually. And so anyway, the next is the instrumentation that we are going to be setting up. We're going to set eddy covariance tower, but also with a 2-point temperature to be able to actually do eddy covariance, but also flux gradient relationship. We're going to be able to determine turbulent fluxes in a kilometer area, which I hope will be the gradient resolution for the mesoscale model, so that we can actually verify the model outputs in terms of the measurements of the scintillometer. The LiDARs, we have one on the campus, but there's going to be another one in the soccer field, and that one is being adapted actually to have another telescope that will look at hopefully from 10-meter height. Okay? And then there's going to be the RPG HAT Pro G5, which is the microwave radiometer that we were able to purchase through the NSF MRI from PDM, Physical Dynamic Meteorology. And then there's going to be a radar coming from LATMOS from France. And then the UAS platform that will have two things. One is one of the anemometers from Aptec from Longmont in Colorado. And then it will have one of the NR01 actually radiometers adapted so that we can look at turbulent fluxes and radiative fluxes away from the towers, but also in the vertical. So therefore, we need as a summary here, I'm wrapping up, we need to get a handle of the buildup of the surface-based inversion, determine with better precision those periods of cooling, the surface cooling and the columnar cooling. Also, the breakup of surface-based inversion requires a little bit of research, actually, in the senses of the radiative forcing induced by the elevated inversions. And then, obviously, improve the description of the energy balance. This is something that we've been working in many areas for probably 30 years, but still causes some elements. We hope that with the UAS, we can unveil some of those, or elucidate some of those problems. And then from my discussions, and obviously I'm not a modeler, but I use model data, it seems that one of the ways that I can think about, because as you can imagine, these radiative boundary layers are basically forced by the surface and eventually by long wave downwelling. But basically it seems that one of the ways to go could be to set up first for the number of days of simulation a land surface model that is forced by the experiments, and then look into closing the model outputs on the basis of determination of structural parameters with the microwave radiometer and LiDAR, and closing up with the boundary layer fluxes based on laser scintillometer. Anyway, so acknowledgments. Yes, I've been supported by the Air Quality Office for WBLEX, and now for the ALPACA PBL, the closure experiment. We are supported by the Physical Dynamic Meteorology Office in NSF, and also for the Major Research Instrumentation Program. And thank you, grad students and ALPACA colleagues, and more than happy to answer any question that you might have. Thank you.
Right. Well, thank you, Javier, for an insightful talk on radiative boundary layers in cold environments. I definitely appreciated all the beautiful winter pictures you've woven into your talk. This is really our first day here in Boulder, where we've had temperatures below 70. So it was nice to see. We have time for questions. We have plenty of time for questions. Again, please use the Slido interface, which is below the presentation screen, if you scroll down to pose your question. And
Yeah, I will say, Jackie, for those actually interested in modeling chemistry, and so I imagine that my colleagues are also present here, Bill Simpson and Jinkyu Mao, and they would be able to answer any of those questions, because there is an array of, I'm afraid, chemistry coming. So, I mean, if any question comes into that.
So I noticed that you for ALPACA, you're going to have a suite of super sites measuring an array of things, and especially in your urban canopy environments, you know, the air over there is dirty. You haven't really talked about aerosols, which, you know, as you know, impact radiative forcing along with temperature. Do you have are you planning to fold in any aerosol statistics in your EI analyses?
Yeah, so this is a question from the public, or?
Nope, this is my question.
Okay, great. Yes, of course, yes. I limited myself to only talking about the meteorology, the dynamics, the turbulence, and the radiation, okay? But there are basically several groups doing ground-based observations using nephelometers, etholometers, using SMPS, scanning mobility particle sizers. And also there are two groups, one from the Cene area in Italy, and so that is going to be coming here with the tether balloon, actually, to look at with OPCs and SMPS within the layers, within the SBI, the surface inversion, and also between the SBI and the EI layers. So we are processing the permission. And also there is another group from Switzerland, from the EPFL, actually, from the Polytechnique Fédérale de Lausanne. That is, so the first one is Stefano De Cesare, and the other one is Julia Schmale. Julia Schmale is from EPFL, and she's coming with an helicite system to actually look at the microphysics of aerosols within those layers. So definitively, this is the opportunity for having these boundary layers and the radiative influence not only resolved in terms of moisture, so in terms of composition, because with the microwave radiometer we're going to have that, but also in terms of more in-depth into radiation due to scattering and absorption of aerosol layers. Yes, of course. Yeah. Thank you for that.
We have a related question, actually, from Sebastian, and he says, thank you for a nice presentation. You are mentioning plans to measure the vertical profile of radiative fluxes, something I'm very interested in as well. What approach are you planning to use?
Okay, thank you, Sebastian, for this, for attending and providing feedback. Yes, the approach to do that is to, well, okay, so there is a colleague from the Finnish Meteorological Institute, David Bruce, actually, who is an expert in UAVs and UAV instrumentation, especially in the polar regions, actually. And so I'm collaborating with him actually to develop to actually do the instrumentation of the UAV. And what we're going to set is the Uptech sonic anemometer, which is a sonic anemometer developed by that company in Longmont, Colorado. I think that they have this since 07, 09, I remember. But this is a sonic anemometer that is very interesting because it has an inertial unit, and so it can be flown, okay? So it has AX, AY, and AZ measurements at 200 hertz. So therefore, that is the anemometer that I will use to put on the UAV. And then I hope to be able to put on, so we are on that, developing the 4 radiometer component on the UAV. So setting up that. Although as everybody knows, actually, UAVs have been used in the very recent experiments, actually, in in the Arctic Ocean actually. But most of the time, people use shortwave radiation sensors because everybody is interested in seeing how the shortwave, how the albedo changes as you go from sea ice to no sea ice. So that's why the approach here is to look at long wave upwelling, long wave downwelling setting on the UAV. And obviously we are going to have to be able to fly. If we fly the radiometer, then we can fly vertical. But if we fly the radiometer and the UAV, then we're going to have to fly horizontal to take both data, okay? And obviously avoid the flow distortion.
Thank you. Thank you for that question. We have a question from Gretchen Mullendorf, and our director of MQ. How close will measurements be in the horizontal in the ALPACA campaign, i.e. how far apart are the vertical profiles? Thank you.
Okay, so there is one site in the boreal forest that has the ecovariance tower and one scintillometer that I have already installed above the boreal forest canopy. That is coming from a NASA funding project, actually, that from previous times. Now then there is another that is a 2 kilometer from that, that is in the farm where we are going to have the ecovariance tower, but no scintillometer there. And then moving into the soccer fields, which is the central area of around the monitoring sites for the chemical sampling. So therefore, again, so it is the urban canopy, but it's an open space, okay? And in there, we are going to install a LiDAR, a backscatter LiDAR, with a dual telescope and right beside the microwave radiometer and also the radar. So therefore, in the soccer fields, which is in the central area within the urban canopy, we are going to be able to monitor not only surface turbulence and the large-scale area average fluxes to do the validation, but also all the profiles with LiDAR, microwave radiometer, and radar. So then, from the soccer field to the two other areas where there's going to be a chemical sampling, there is probably a 1 kilometer or probably no more than 2 kilometer distance. Now, within the soccer fields, the group from Italy will also be developing the tether balloons, actually, to do the high resolve OPC, optical particle counter, and SMPS measurements of the aerosol microphysics. The group from IPFL, actually, in Switzerland, will go to the North Pole area. And in the North Pole area, we are going to have the surface fluxes, the scintillometer, and the vertical. So anyway, so yeah, so we have a limited number of profilers. So, but I think that we can. I mean, the first idea I have was to look at what are the surface turbulence and radiation constraints, so that to run the land surface, adjust the land surface model, and then ingest that into the mesoscale model. But this is something that it would be good to discuss with Gretchen, and also I'm interacting with Mike Eck, actually, that is from from Anchor. He also has some other ideas as well. So anyway, yeah.
Thank you for that question. Javier, you described a very intense campaign. Is it running for multi-years? When does it have an official start and end time?
Yeah, January 15 is going to be the starting. But then it will go all the way to the end of February. But I am in the process of developing an analysis proposal that probably will include another round of measurement the next year, mostly dedicated to turbulence, radiation, and dynamics. And so yeah, and this is in the so if we, because obviously one thing is the central part of the winter, and the other are the shoulders. We call this the shoulder season. You might never hear that, but shoulder seasons are when you get out of the winter or when you're coming in, like right now. And so in those shoulder seasons, you have, like right now, uncovered surfaces, but on the other side, when the winter is ending, you have covered surfaces. And then surfaces that change from snow to water. So therefore the heat capacity is totally different. And therefore, all those fluxes and parameterization probably, we will have to deal with. It's a very complex environment.
Well, we'll have to have you or your postdocs back post-ALPACA to give an overview. It seems like you'll be drowning in a rich data set. Well, if we don't have any further questions for Dr. Javier Fochesatto, we are near the end of the seminar series. So if you are interested in his presentation and have further questions, please reach out to him via his email, which is provided in the seminar flyer. On behalf of VOL, I would like to thank Dr. Fochesatto on his excellent and informative presentation on cold nighttime boundary layer inversions. Thank you, everyone, and I hope you have a good day.
Thank you, Jackie, and thank you, Brett.